Hi everyone, thank you for coming to my presentation. I'm Nguyen, and today I'm presenting to you our latest work, VideoFACT, detecting video forgeries using attention, scene context, and forensic traces. Detecting fake and manipulated contents is critical to prevent misinformation, online fraud, and many other threats. Nowadays, with the invention of hardware accelerators and advanced deep learning techniques, there exist many AI-based video editing methods, such as deepfakes, as you see on the left, and in painting, as you see in the middle. Additionally, while media attention has focused on these algorithms, we cannot forget that forgeries created with traditional video editing software exist and are more prevalent due to the lower entry barrier. Researchers have devoted much effort to create algorithms to analyze images and video. These algorithms can be divided into two groups: the specialist detectors for video, such as deepfake detectors and in-painting detectors, the generalist detectors for images. However, there currently exists no generalist detector for video capable of identifying multiple forgery types. As seen in prior work and in this work, existing detectors for video only work on one manipulation type, and image manipulation detectors all fail on video. The reason why general image manipulation detectors fail on video is due to the effects of modern video coding. These detectors work by extracting forensic traces from different regions of an image and look for inconsistencies among these traces. At a high level, a forensic trace represents the relationship of a pixel with its surrounding, and if we look at a group of pixels in an analysis window, these relationships reveal the processing history of that analysis block. However, as we see in this illustration, modern video codecs encodes each macro block dynamically, causing each macro block having different compression parameters. This is detrimental because it naturally induces inconsistencies within a frame, causing all image detectors to fail. To address this problem, we propose VideoFACT, a new network capable of detecting and localizing a wide variety of video forgeries. At a high level, our network first captures forensic features specific to video. Then we learn new context features to control for variation in forensic traces caused by video coding. Then we create a set of joint feature embeddings that are analyzed using a deep self-attention module. We then refine the joint feature embeddings using attention map. And finally, we produce accurate decisions using separate subnetworks for detection and localization. Here are the details of each of the network components. The low-level feature extraction component has two types of feature embeddings. The forensic feature embeddings designed to capture traces specific to video. The context feature embeddings learn to control for variation in forensic traces caused by video coding. And the joint feature embedding, which are made by concatenating these two embeddings. The deep self-attention module purpose is to estimate the quality and relative importance of local embeddings by de-emphasizing regions of low-quality traces and emphasizing regions with high-quality traces and potential manipulation. The attention-informed feature refinement module refines the joint feature embedding by using the attention map resulting from the prior module to scale embedding vectors by its respective weight. This enables accurate decision-making while minimizing false alarm due to video coding. The detection subnetwork combines refined embeddings into detection 4, and the localization subnetwork distills refined embeddings into patch-level localization map, which is converted into a pixel-level localization map using bilinear interpolation and smart thresholding. To train and evaluate our network, we look for multi-manipulation datasets. However, no large datasets of this type exist, except for Adobe VideoSham, which we use for evaluation only. And we created two types of datasets, the standard video manipulation dataset and the in the wild dataset. The standard video manipulation dataset contains simple video forgeries like splicing and editing, and the in the wild datasets contain in-painted videos using state-of-the-art in-painting algorithms and deepfake videos using Deepface Lab and others. To train our network, we employ a multi-stage training protocol. This is to improve generalization through unseen manipulation, which we'll show in our experiment, and to improve convergence during training. Our protocol can be divided into two major steps. First, we pre-train the forensic feature extractor on the camera identification task using video asset dataset. Then, we progressively train on increasingly challenging manipulations, from video camera model splicing to video perceptually visible manipulation to video perceptually invisible manipulation. Note that we do not train on deepfake or in-painting. To evaluate our network, we benchmark against state-of-the-art general image forgery detectors and specialized video manipulation detectors. Using two sets of datasets that we discussed earlier, the standard video manipulation dataset and the in the wild video manipulation dataset. We reported performance with MAP and accuracy for detection and MCC and F1 for localization. Here's the result. On splicing and editing, we obtained very strong detection and localization performance on all three datasets in the standard video manipulation dataset. And we can see that existing detectors largely fail. On in-painting, our baseline model, which has not trained on any in-painting data, obtained good detection and localization results. We also present VideoFACT fine-tune, a fine-tuned version of our baseline using a very small number of examples. This achieves excellent detection and localization results. And again, we see that existing approaches largely fail. Here we present a result on Adobe VideoSham. Adobe VideoSham contains multiple types of manipulation, color swapping, object addition or removal, text addition or removal, etc. Note that VideoFACT has not trained or fine-tuned on any of this data. However, we still retain the strongest reported results. On deepfakes, however, the baseline VideoFACT performance is mixed. However, we present VideoFACT fine-tune. In this experiment, we fine-tune only 10% of DFT and FF++ dedicated training data. And after we did this, we obtained excellent detection and localization results. And we can still see that splicing detector largely fails. On some occasions, we even outperform existing deepfake detectors in this experiment. Here are the key takeaways. We are able to detect and localize a wide variety of forgery types. We significantly outperform SLTA image detectors. We can also massively improve performance by fine-tuning on a very small amount of data of a specific manipulation. This is important because the number of manipulation types is increasing and because the type of manipulation is not known a priori in the real world. Our network performs best when the falsified region is larger than our analysis window size. The forgery and its surroundings does not suffer from poor lightning or texture. Color swapping in optics can still be challenging to detect in our network, and our network input size is still limited to 1080p video resolution at this moment. We also conduct a comprehensive study to prove the effectiveness of individual components in our approach, as seen in here and in our paper. And thank you very much for listening to my presentation.